Today we're going to see two more uses of the dot product. The first of which is to calculate the angle between two vectors. And the second of which is to take a vector and to break it down into pieces. One of which is parallel to some given direction and one of which is perpendicular to that direction. To get started on the first application, let's consider the following formula that can be used to find the angle between two vectors. Now, first, I just want to remind us of the meaning of the notation, the vector v, with vertical bars around it. This is our shorthand for the magnitude of the vector v. The length of the vector v, which can be found using the Pythagorean theorem, or equivalently using that formula when we were dealing with polar coordinates. If we want to find the angle between two vectors v and w, then that angle, theta, is equal to arc cos of the following quantity. In the numerator, take the vector v and dot it with the vector w. Then divide that by the magnitude of the vector v, and divide that by the magnitude of the vector w. Now, to make a quick note, the angle between the vectors v and w is not the same as the direction angle of the vector v, and is not the same as the direction angle of the vector w. If I were going to represent this pictorially, here maybe is the vector v, and here maybe is the vector w. The angle theta given by this formula is the angle that lies directly between these two vectors. It is not the angle of the vector v, and it is not the angle of the vector w. This is the angle which is between the two vectors v and w. Let me give you an example of the calculation of the angle between two given vectors. So in this case, we have a first vector which is called 2, 1, and we have the second vector 3, 5. So let me just nickname this first vector v and this second vector w. The first thing that I'm going to do is I'm going to calculate the value of the dot product. So I'm going to take the product of the two x's, and I'm going to take the product of the two y's. So that would be equal to 6 plus 5, so that would be equal to 11. The next thing that I'm going to do is I'm going to find the length, the magnitude of the vector v. Now, magnitude squared is equal to x squared plus y squared. So the magnitude by itself must be equal to the square root of x squared plus y squared. So 2 squared plus 1 squared is 5. So the magnitude of v must be equal to square root 5. We'll also need to find the magnitude of w, which similarly can be found by taking the square root of 3 squared plus 5 squared. So that's 9 plus 25 underneath the square root. So that's the square root of 34 in total. So now, what is the angle theta? The angle theta can be found by applying inverse cosine to the fraction which has the dot product in the numerator and the two lengths in the denominator. So let's go ahead and use a calculator to find a decimal approximation for this angle, 32.47 degrees. So let's make a quick sketch just to check and make sure that this result makes sense. Here is the xy plane, and here is a loose sketch of the vector v. And going 3 over and 5 up, Here's a rough sketch of the vector w. And here is the angle theta that we are asked to calculate in this problem. And just based on the sketch, this value of roughly 30 degrees does seem plausible based on the amount of separation between v and w in this picture. So, seems about right. This time let's find the angle between the vectors -3, 1 and +1, 2. In this case, once again, I'm going to start by finding the dot product of these two vectors. -3 plus 2 result -1. Let's find the length of the vector v, which is equal to the square root of the x component squared plus the y component squared. So that's equivalent to the square root of 10. And let's find the magnitude of w, which is equal to the square root of the x component squared plus the y component squared, which is equal to the square root of 5. So the angle between these vectors, theta, would be equal to arc cos of the dot product divided by the square root of 10 times the square root of 5. So let's get a decimal approximation for that value. This works out to be approximately 98 degrees. Now let's see if that answer makes sense based on a quick sketch of this situation. In this case, the vector v points to the left side of the xy plane, hereabouts, whereas w points over here. So it does make sense based on the picture that the angle that we found is just a little bit larger than 90 degrees. That does seem plausible here. Notice that because the formula that we're using contains an inverse cosine, it is completely possible for us to get angles which are larger than 90 degrees. That's one of the real benefits of working with inverse cosine, is that it can produce obtuse angles. Now there's a quite simple way to determine whether the angle between two vectors happens to be exactly 90 degrees. In other words, to see whether the two vectors are perpendicular. Now, if the angle between the two is exactly 90 degrees, then 90 degrees would be equal to inverse cosine of v dot w divided by the length of v and the length of w. So suppose that I took this equation and applied cosine to both sides. And this would be equivalent to cosine of 90 degrees is equal to v dot w divided by the length of v and the length of w. Now what is cosine of 90 degrees? 90 degrees is at the very top of the unit circle where the x coordinate is 0. So this would be equivalent to saying that 0 is equal to v dot w divided by length of v and length of w. Let's multiply both sides by the two magnitudes. But of course, any number times 0 is just equal to 0. So after simplification, I get the following result. If the two vectors v and w have an angle between them that's equal to exactly 90 degrees, then as a consequence, the dot product between those two vectors is 0. So this gives us a really quick way to check and see whether two vectors are exactly perpendicular. If the dot product is 0, then the vectors are perpendicular. As a quick example, if I had, for example, 1, 3 and 3, -1, and someone asked, are these perpendicular or not? it would be incredibly straightforward for me to answer that question. Because I could just take the product of the two x's and the product of the two y's, add the results together, and yes, the result of that is 0. From this, I can conclude, without any pictures or even having to think very hard, that these two vectors do form a right angle with each other. You have some vector called v, and then you have some other direction, maybe call it u. And the goal is to figure out, okay, what part of v, what portion of v is aligned with u? And what portion of v is exactly perpendicular to u? The idea is to project, literally like one of those old-fashioned overhead projectors, to project v onto u, and to see what shadow v casts in the direction corresponding to u. This shadow of v on the surface on which u lives, this is the part of v which lines up with the vector u. And this is what we call the projection. The projection of v onto u. Now if I look at sort of the vertical leg of the right triangle that I am forming in this drawing, then this is the other part of v, which is perpendicular at a right angle to the direction indicated by u. So projection is a technique for taking a vector like the one called v here and splitting it up into the portion of v which aligns with u and the portion of v which is perpendicular to u, as in this image. Now the formula for the projection of v onto u is given by the following. If I want to project v onto u, the notation for that is proj for projection, and then a large V, and then underneath V to the left, the vector that you are projecting onto. So onto u in English, the projection of V onto u, the u in the notation shows up as a subscript underneath projection and V. Now, how do I calculate this quantity? I calculate this quantity by first of all calculating a scalar, calculating a number. And that number is equal to v dotted with u divided by u dotted with itself. Because the dot product in the numerator is going to output a number, and the dot product in the denominator is going to be a number. This entire fraction, number divided by number, this whole thing is just a scalar. Now I'm going to use that scalar to scale the vector u. So be careful, the projection of v onto u is quite different from the projection of u onto v. When you project onto u, u shows up in the subscript of the notation, and in the formula, u appears a total of 4 times. Once in v.u, twice more in u.u, and then the 4th time is you take this number and use it to scale u. Here we have v is equal to 1, 1, and u is equal to 3, 0. So let's calculate the projection of v onto u, which is represented in text as projection, proj, with a large V and a small u. Once we've finished doing that calculation, they would like us to draw all 3 of the vectors u, v, and the projection on the same axes. So I'll start by drawing the vector u, which points 3 units exactly in the x direction. And I'll draw the vector v, which points 1 unit in the x direction and 1 unit in the y direction. So we're looking for the portion of the vector v which lines up with the vector u. In other words, we're looking for the portion of the vector v which, in this case, aligns with the x-axis. Now let's calculate the projection using the given formula. To use the given formula, the first thing that we need is the value of the dot product of v and u together. So that's 1 times 3 plus 1 times 0. That's 3 plus 0, which is 3. We're also going to need u dot u. So that's 3 times itself, 3 times 3. And 0 times itself, 0 times 0. So that's equal to 9. So now, let's take the number 3 divided by 9, v dot u in the numerator, u dot u in the denominator, and use that to scale the vector u that we are projecting onto. So that's 1/3 times 3, 0, which is the number 1, 0. So let's see which portion of v lines up with u in this exercise. If we were to graph the projection on these axes, we would get the literal shadow of v cast onto the x-axis, which is the direction in which u lives. This is the projection onto u of v. Let's try it again with a twist. This time v has a negative x component. So here's the vector u, but this time v is pointing to the upper left. Now in this case, v dot u is equal to -1 times +3 plus +1 times 0. So that's equivalent to the number -3. Now the vector u has not changed from the previous exercise, so u dot u is not going to change either. That's also going to be equal to 9. Let's take that number, -3 over 9, and use it to scale the vector u. So that'll be equal to -1/3 times 3, 0. So that's going to be equal to -1, 0. Make sense that that vector is the shadow of v, the shadow as cast onto the x-axis being the line that contains u. So here, this vector in red, the projection, is the portion of v which aligns with u. In this case, they point in opposite directions, but they do still live on the same line. In this case, both the projection and u live on the line, which is the x-axis. Now to show how much order actually matters in these calculations, let's take the vectors v equals 1, 1 and u equals 3, 0. And in this case, let's find the projection of u onto v. Let's find the portion of u which aligns with the vector v. Now for this projection, u onto the vector v, where v is the subscript, I'm still going to calculate the dot product of u and v together. And the result of this is 1 times 3 plus 1 times 0. So the result is still equal to 3. However, because I am projecting onto v this time, I need to calculate the dot product of v with itself. Onto v, so v dot v, which is equal to 1 times 1 plus 1 times 1, which is equal to 2. Because I am projecting onto the vector v, I'm going to take the number 3 over 2 and use it to scale v. I'm going to use it to scale the vector that I'm projecting onto. So this is equal to 3, 2 for both the x and y coordinates. This would be the projection of u onto the vector v. So in this case, the projection is, roughly speaking, right around here. The projection onto v of u. This is the portion of u which lines up with the vector v. Now the projection is used to break a vector down into parts. For example, here we can break the vector u down into 2 parts. One part, the red vector, formed by the projection of u onto v. This is the portion of u which is lined up, which is parallel to the vector v. And a second portion drawn here in white, which is perpendicular to the vector. Added together the red vector and the white vector, if I added these vectors geometrically, then the result of that sum would be exactly equal to the green vector u. So projection is basically a way of undoing vector addition, taking a vector u and breaking it down into parts. Suppose that I have 2 vectors here called v and w. If I took the vector v and projected it onto the vector w, this would be the portion of v which aligns with the vector w. Now suppose that I took the vector v and then subtracted the projection. I took the vector v and then removed all the portion of v that was lined up with the vector w. Then the leftover would be the portion of v which is perpendicular to w. To give you one quick example where you might see this come up in physics, we have gravitational force acting on a 1 kilogram object, and this can be represented by the vector which has a 0 in the x component and a negative 9.8 in the y component. So we have gravitational force which is acting straight downward, and then we have an object which is resting on a plane, and the slant of the plane is such that it can be represented by the vector that points 1 unit in the positive x direction and 1 unit in the y direction. So let's figure out, first of all, the portion of the force vector which aligns with the plane. Now to figure out the portion of the force vector which aligns with, which is parallel to, the plane represented here by the green vector, I'm going to find the projection of the force onto the green vector, 1, negative 1. Now to find the projection, I'm going to start by taking the force vector and dotting it with the vector 1, minus 1. In other words, I'm going to take 0, negative 9.8 and dot it with the vector 1, negative 1. So the result of that is going to just be equal to the number positive 9.8. I'm also going to take the vector that I'm projecting onto and dot it with itself. So that's 1 times 1 plus minus 1 times minus 1, result 2. So now I'm going to take the number 9.8 divided by 2, and I'm going to use it to scale the vector that I'm projecting onto. So that is going to be equal to what works out to be 4.9, negative 4.9. This is the portion of the force which acts in a direction which is aligned to the plane represented by the vector 1, minus 1. So that would be about here. So then the question is, all right, what is left over? If the projection represents the portion of the force which acts in a direction that is lined up with this plane, what's the portion of the force that acts in a direction which is perpendicular to this plane? So to figure that out, all I need to do is take the force vector and remove the portion that is lined up to the plane. Force vector minus 4.9, negative 4.9. So this works out to be the vector negative 4.9, negative 4.9, after completing this arithmetic. So that vector, roughly speaking, is right about here, drawn in white. Perpendicular portion. So this can be used in physics to break a force down into parts. For example, here, gravitational force can be broken down into what portion of gravitational force is moving the object down the plane, and which portion of gravitational force is basically just smushing the object against the plane. That concludes today's material. We looked at 2 more applications of the dot product, the first of which was to calculate the angle between 2 vectors. And in particular, if you dot 2 vectors and get 0 on the nose, then those 2 vectors are at a 90-degree angle. They are perpendicular to each other. We also saw how to use the dot product to project one vector onto another, to see what portion of a vector lines up with a specific direction and which portion of the vector is perpendicular to that specified direction.